All right, so yesterday we finished off talking about how to identify unique protons and unique carbons, and we said you really have to determine whether or not the atom you're looking at is in the same chemical environment as another atom, right? So if it's in the same chemical environment, you only observe one signal, even if there's multiple protons making up that signal. And then we said if you've got nuclei in different chemical environments, you'll see a resonant frequency corresponding to each unique set, and we went through a couple examples there. And then we kind of finished off talking about this example where we said not only can you determine the number of unique signals, but the size of the signals corresponds to the number of unique protons that make up that signal, right? So let's talk about that in a little bit more detail. So in this example, we had tert-butyl groups on each side of the benzene that were equivalent. We had 9 total protons making up those red squares, so we said the relative size of that red peak should be about 18. And that's compared to the relative size of those blue protons that have a peak size of about 4. Those are called integral values. It's the area underneath the peak. So what I want you guys to do is to help me with a different example. And I want you to determine the number of unique protons and the relative integration for the set. All right, so I'll give you guys an example. And I would caution you to check with your neighbor and see if you're agreeing with the number of unique protons in this before you talk about integrations. And then once you think you've determined the number of unique protons, show me with your fingers how many you think there are. Show your fingers proud. You don't have to show me a middle finger, though. I see some 2s and some 4s. Is that what most people are coming up with, is either a 2 or a 4? Or 1?
No.
Oh, okay. All right. I'm going to argue that there are only 2 unique proton sets in this molecule. A lot of people are tempted to pick 4 because they say, you know what? There's a plane of symmetry going smack up and down this molecule. However, symmetry elements can't always be planes, right? There's also rotational symmetry. So what happens if we rotate this clockwise a little bit? So I'm going to label this A, B, and C. If we rotate this, right, I can rotate it so that A is down here, B is over here, and C is over here, but that's the exact same molecule, right? So if we think about that methyl group that I've labeled A, it's occupying the same chemical environment as the methyl group I've labeled in B. So there's actually rotational symmetry in this molecule, which is a little bit different. That's something you also have to watch out for, is not only planes of symmetry, but rotational symmetry elements as well. So we know we've got 2 unique proton signals, and I'm going to go ahead and draw out the protons. So we've got 3 protons here, 3 protons here. We know all the methyl group protons are identical due to rotational symmetry. So I'm just going to label all of these HA. And then last but not least, we also have these protons coming off of the benzene ring, and these are also equivalent due to rotational symmetry. So I'm going to label these protons B. All right, so we should only have 2 unique proton signals. All right, so I'm just going to come up with a list. I really like making lists with NMR. So if we look, I'm going to call this HX, sorry. If we look at proton A, what should the integration be for proton A? 9. Okay. And HB should be what? 3. So if we look at the NMR for this, we've got this scale that we talked about yesterday that's measured in parts per million. The zeros on the right, you typically go up to about 12 to 15 on the left. We would have a big peak over in this region corresponding to A. And oftentimes what you'll see with NMR is this integration symbol that looks like this. And basically that tells you the size of the peak. And usually a computer will spit out a number corresponding to the relative ratio of that peak. And if we think about HB, HB is going to show up in this NMR spectrum. And HB is going to be at a different resonant frequency, and it's going to be about 1/3 as big, right? Because we've got 1/3 as many protons making up the signal. So I'm going to go ahead and label this, and I'm going to say the integration value here is a little bit smaller. In fact, let me do something like that. So this is a ratio of 9 to 3. We could also have 900 to 300. We could have 9 million to 3 million. It's really just a ratio, right? We could just say 3 to 1 for that matter. It's not a definitive count of the number of protons in the signal. It's just saying these are the relative peak sizes relative to one another. That's a really important concept that students oftentimes forget, is they think that it's the computer telling you the absolute number. It's not. It's just a ratio. Does that make sense? All right. Unfortunately, NMRs aren't as simple as this. Right now, we've been seeing NMRs where you only have peaks that are nice, plain old vanilla peaks. The reality is, in NMR spectra, you oftentimes get what's referred to as peak splitting. So let's talk about that. So this is a kind of abstract concept. And it's based on the fact that nuclei can be spin up or down. And they can have spin-spin coupling with neighboring nuclei. And so I'll show you guys a simple way of understanding coupling. And let's take a look at a really simple example. So let's look at how HA affects HB. In fact, I'm going to color code this since I can. So I'm going to say HA is red and HB is blue. And let's come up with a nice list to show how they affect one another. So let's say we've got a carbon-carbon bond and we've got HA coming off one of the carbons and HB coming off the other. So I've got HA on the left and I've got HB on the right. And then in my other column of my chart, I've got possible HB HA spin states. Or actually, sorry, let me rephrase this. Let's just do HB spin states. I don't want to overly complicate things. So if we look at HB here, we know it can be spin up or spin down, right? So what I'd like to do is just show this using squares. So HB could be either a nucleus that's relatively spin up, or it could be relatively spin down. And the ratio of it being spin up to spin down is going to be what? 50-50. It's an even chance. So oftentimes, if you've got one neighboring proton, your peak will be split into what's referred to as a doublet. Because that neighboring proton could be in two different orientations. It could be in either spin up or spin down state. And a doublet looks a little bit funny, but it looks like a pair of fangs. And typically, it's pretty small. Whoop. Make this a little bit more clear. And people oftentimes just abbreviate it as a D to help simplify things. Now let's look at a more complicated example. And for this one, we're still going to...
Can I ask a question real quick?
Yeah.
Why are we looking at peak for HA in comparison to the spin of HB?
So HA, that's a good question. HA feels HB, but HB can be in two possible states, either spin up or spin down. So that causes the HA signal to actually appear as a doublet. It's a little abstract to think about, but that HB is impacting the signal of HA and splitting it into two possible peaks that are really, really close to one another.
Okay.
Now let's look at a more complicated example. Let's say we've got two neighboring protons in that HB position. So HA is still over here, but we've got two HBs. Now things get a little bit more complicated because we've got two HBs, right? Both of them could be spin up, so that's one probability. So I'm going to say, all right, that's possible. Another option is one could be spin up and one could be spin down. So I'll say that's also probable. Or it could be flipped. The one that was spin up could be spin down, and the one that could be spin down could be spin up. But really the net impact of this is going to be the same, right? Because one spin up and one spin down in either situation. Or last but not least, both could be considered spin up. Or sorry, spin down. We already did spin up. All right, so if we look at the ratio here, it's going to be a 1 to 2 to 1 ratio of our peaks being split, right? So if we look at the top example, we had a doublet because it was a 1 to 1 ratio. What do you think we'll probably call this peak? A triplet, exactly. And so a triplet is kind of cool. It looks a little bit like a mini trident. So HA doesn't appear as a singlet, doesn't appear as a doublet. Because it's got two neighboring protons, it's split into a triplet, which is oftentimes abbreviated as a T. We'll do one last one. And with this one, let's imagine if we've got three neighboring protons. Now the statistics become a little bit more challenging. So HB, all three of them could be spin up. That's one probability. Alternatively, they could all be spin down. So I'll put these over here. That's another probability. Or we could have two up and one down, right? However, there's a couple ways to orient this. So if we have two up, one down, it could be the two left-hand ones that are up, or it could be the two edge ones that are up and the middle one down. The net of these is both two up, one down. Or we could have the left one down and the right two going up. So there's three possible ways to get this combo of having two up and one down. There's also three possible ways of having two down and one up. So let's do the opposite one. So in terms of the probabilities here, the probability of having all three of them spin up is a probability of 1 versus a ratio, or a 1 to 3 ratio of them all being up versus 2 being up, 1 being down, to 3 to 1. You guys kind of follow this ratio pattern? So in this case, this peak is going to be split into a 1 to 3 to 3 to 1 triplet, or sorry, quartet, where the smallest peak on the edge is going to be 1/3 the height of the inner peak, and the two inner peaks are going to be about the same height, and then you're going to have a little peak on the outside. What do you think happens if we've got 5 neighboring protons? Or sorry, 4 neighboring protons. We'll go in order. So imagine if we have 4 HBs, what peak would HA be split as?
1, 2, 3, that's 4.
It gets kind of complicated, but luckily, I've got a handout for you guys. This handout that I gave you guys shows the approximate splitting pattern for each of these. So if you've got neighboring protons, you typically are looking at 3 bond neighbors or 2 bond neighbors, right? So if you guys see the HBs that I drew, they were 3 bonds away from HA. And if you have no neighboring protons, your peak isn't split at all. It will show up as a nice singlet. If you've got one of those neighboring protons, like we saw with HB, it's going to be split into a doublet. If you've got 2 3-bond neighbors, it's going to be split into a triplet. 3 3-bond neighbors, it's going to be split into a quartet. 4 will be split into a pentet, and the pattern gets more complicated. It's now 1 to 4 to 6 to 4 to 1. And then if you've got 5 3-bond neighbors, you can observe a sextet. If you've got 6 3-bond neighbors, it will be called a septet. And if you've got so many that you are losing track of what's going on, chemists get lazy and they just say, you know what, this is a multiplet, which basically is a fancy word of saying there's too much for me to deal with right now. So oftentimes you'll see these unique splitting patterns, and they tell you quite a bit about the location of that proton, because that splitting pattern tells you how many neighboring protons are 3 bonds away from the proton you're looking at, right? So for example, if you see a peak that's split as a doublet, that means it has 1 neighboring proton that's 3 bonds away. That's a really good structural tool you can look at. So let's go back to our lecture material and make a couple of notes. So HA is a proton we're investigating in this situation. Can only feel, I'm using feel in the non-literal sense, protons that are 2 or 3 bonds away. Typically, the amount of splitting that occurs drops off pretty dramatically the further away your neighbors get. As soon as you're 4 bonds away, it's too far for them to really feel or interact with any other proton in a significant way. So really, when we're investigating things, try to focus on 3 bond neighbors, and on occasion, you want to focus on 2 bond neighbors as well. There's also another important rule, and that is protons that are identical can't split one another. So HA cannot be split by other HAs. So let's go through and do some examples, and I want you guys to help me predict the splitting pattern for an example molecule. Okay, and we'll do our favorite example, ethanol. And I want you guys to first determine the number of unique proton signals that we should observe, determine their relative integration size, and then when you're all done with that, determine how each peak should be split. And I'll show you guys how I do this typically. I do HX, and then like before, we do the integration ratio. And then we're going to add in a new column for splitting. So let's first identify all of the unique proton sets that we have. And then show me with fingers how many protons you think there are. Oh man, you're doing the German 3. 3? All right, I think we've all got 3. So if we look over here, we could say, all right, these are HAs, right? Those are all equivalent HAs. The next one over, we could say these are HBs. And then last but not least, we've got this coming off the end. I'll call that HC. And then we'll fill this into our list. So we've got 3 unique sets, and I'm going to color code them. A, we've got B, and we've got C. All right, relative integration for HA. What should it integrate as? What's the size of the peak? So HA? We've got 3 protons making it up, right? So the relative size of the peak will have a relative size of about 3. Versus HB, which will have what relative size? 2. So it'll be a little bit smaller than the peak that we should see for HA. And then HC should have what? 1. Okay. All right, now let's do this. Let's do the splitting pattern. If we look at HA, how many 3-bond neighbors does it have? And most people got that pretty quick. It's got 2, which means it's going to be split as what? A triplet, exactly. So HA will have a relative integration size of 3, and it will be split as a triplet. All right. And then if we look at HB, things get a little bit more complicated, because with HB, you could say those HAs are 3-bond neighbors, right? And HC, you could argue, is a 3-bond neighbor. However, there's one problem, and I'll show you guys this. This is an important thing, so I'm going to use a special pen. We'll use the glitter pen. There we go. You can't, you can't count 3-bond neighbors through non-carbon atoms. It's kind of a brick wall. That HB can't feel HC. The oxygen's in its way. It won't split at all due to HC. So if we look at HB, we don't want to count HC at all. So how many 3-bond neighbors does HB have? 3. We can only count the 3 HAs. We can't count HC because it's going through an oxygen atom on its way. So if we look at HB, what will it be split as? A quartet. All right, and then HC, if we look at it, How many 3-bond neighbors does HC have? 0. We can't go through that oxygen atom. It's a brick wall. So if we look at HC, it's got 0 3-bond neighbors, which means it will be split as a singlet. All right, now let's see if our example checks out. I'm going to move this up and blow it up. All right, this is the NMR spectrum that's observed for ethanol. And if we look at it, this peak right here is our quartet. What does it integrate to if it's our quartet? Let's go back up. We said that our quartet should have a relative integral size of 2. So we'll say quartet 2H. And then I'm going to label this as H what? A, B, or C? B. We said HB, so I'm going to go ahead and say this has got to be the signal from HB because it's the only quartet that's showing up in our spectrum. Does that make sense? If we look over here, we've got a singlet. That's got to be that proton HC coming off of our alcohol. So I'm going to call this 1H. And that means that this peak must be HC. And then last but not least, just to round things out, we've got this triplet closer to 1 ppm. And this is our triplet. And it's a pretty big triplet because it's got 3 protons making it up. And this is HA. So oftentimes as chemists, you have to predict what you think your NMR spectrum would look like and then match that to theory, right? So the best way to really convince yourself is to predict it, take your NMR, and see if it matches. If it doesn't match, that's a good clue that maybe you didn't make what you thought you made. So this is an excellent way of confirming the identity of a compound if you're making something new. Does that make sense? You guys want to try another one? Okay. This one I want you guys to do in a group. And let's just focus on filling out our chart. So we're going to do that HX, the integration, and then the splitting. And let's just focus on protons right now. And I'm going to draw in all of my protons. I've got a lot of protons on this guy. Or girl.
Or non-living entity.
I like to personify my molecules. How many unique proton signals do you guys think there are? Show me with your fingers. See some 4s and some 3s. Check with your neighbor and see if you agree. So is the consensus 4?
Yeah.
Yeah. The reason that there's 4 is we've got a plane of symmetry in this, right? Vertical plane of symmetry cutting the molecule in half. So if we look at this, let's just label them again. So I'm going to start down here, and I'm going to say HA is the same as this guy. HB is the same as this one. HC, we know the methyl group spins around like a helicopter blade. And the methyl group on the other side is identical. So I'm going to label all these HC. And then last but not least, we got this little guy down here, HD. All right, so let's go ahead and label this. In our chart, we've got HA, HB, HC, and HD. All right, HA, integration size. How big should the peak be? 2. All right, HB should have what peak size? 2. HC should have what peak size? 6. And then HD, 1. All right, now let's go back and determine the splitting. This is the tricky part. If we look at HA, just focus on one of them. Even though there are 2 protons, they're chemically equivalent, so we might as well just cover up one half of the molecule and only focus on the other half, right? So in this case, HA should be split as what? A doublet, right? If we look at HA and we cover up half of the molecule, so for example, I'm going to say ignore these guys. HA has one 3-bond neighbor, that HB, so it's going to be split as a doublet. So let's go ahead and write that down. All right, HB. What will it be split as? How many 3-bond neighbors does that HB proton have? This is tricky, right? Let's go ahead and try to trace our paths, right? So HB, we could go 1, 2, 3. It's 3 bonds away from HA. A lot of people say, well, what about HD? In order to get there, it'd be 1, 2, 3, 4. We said 4-bond neighbors don't count, so HD won't impact HB at all. So HB will be split as what? A doublet. All right, and then let's do HC. How many 3-bond neighbors does HC have? Just 1, right? We've got that HD proton that's 3 bonds away. So this will be split as a doublet as well. And then the crazy one, HD. How many 3-bond neighbors does HD have? HD has 6 3-bond neighbors. So what will it be split as? Septet. Septets are pretty funky looking. And this will be a little itty bitty guy because it's only got an integration of 1. So then the question is, you know, we've got this NMR scale from 0 to about 15. And I'm going to put 10, and I'm going to put 5 here. And the question is, well, is our septet going to be kind of in this region? Is it going to be over here, or is it going to be down here? We need to find a way of predicting where that septet is going to fall from 0 to 15. That's where that handout comes in handy, right? So let's take a look at the handout that I gave you guys. And it's on the front page of this handout. And right now, I only want you guys to worry about proton NMR. If we look at this, we've got to kind of figure out where it falls, and this tells you some rough guides for how to predict where a proton will fall on your NMR spectrum. So if we look at that HD proton, that septet, it's coming off of an sp3 hybridized carbon, right? So if we look at this one, it's definitely not coming off of a carboxylic acid, so it's not going to be in this range from about 10 to 12. It's not coming off an aldehyde, so it's not going to be here. What does AR mean?
Argon.
Normally as an element, it's argon. Aromatic. So it's short for an aromatic ring, meaning it's coming off of benzene. So it's not coming off of an aromatic ring. We do have other protons that are, but not that HD one, the septet that we're concerned about right now. So we could say it's not going to show up in this region. It's not coming off in alkenes, so it's not there. It's not coming off in oxygen. It's not coming off in alkyne. It's not coming off of the alpha position of a ketone. It's not a methyl group that's coming off of an aromatic ring, but it's pretty similar. It is on a carbon directly attached to an aromatic ring. So if I look at this, I would predict that that septet should probably fall in the range of about 2 to 3 ppm. So let's go back in and try to fill out our predicted NMR. And I'm going to put it in right about here. I'll do my best to make a septet. And we could say this is our septet. It's got an integration of 1, so I'll say 1H. And it's between 2 to 3 ppm according to that handout that I gave you. All right, where do you think HC might show up? The methyl groups. Yeah, right around 1. So I'm going to slide this over, and I'm going to say, whoop. We should have a big old doublet close to 1. And this doublet's going to be significantly bigger than our septet. And this will be doublet 6H, approximately 1 ppm. All right, so we've taken care of the top half of our molecule. Where do you think HB might show up? Yeah, around 8 to 7 ppm. Okay, and it's going to be a lot smaller than that doublet on the far right. It's going to be roughly 1/3 of the size. So between 8 to 7 ppm, we should have a doublet for HB. And we should also have a doublet for HA. So I'm going to go ahead and draw these. I know the size. Let me try to fix the size a little bit. This will be a doublet, 2H, 6 to 9 ppm. This will be a doublet as well, also 2H and 6 to 9 ppm. This is what our predicted NMR would look like. This is really similar to what I want you guys to do on the pod, right? So the first thing you need to do on your pod is determine the number of unique proton sets that you have, the relative integral size, and then the splitting pattern for each unique set. And then on the bottom it said to actually draw out the predicted NMR spectrum, really similarly to what we've done here. So for the last couple minutes, I'll give you guys time to work on that pod. And if you guys have any questions, I'll be floating around the room.